Welcome to yet another lecture on power generation and economics. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Degree Engineering College, Electrical Engineering Department. Previous class, we have seen that how we can form the load curve and what are the outputs from a load curve means daily energy produced, load factor, average load demand, and the maximum demand can be obtained from a load curve. Today, we will also see some numerical problems which are related with economical power generation. So how we can able to draw those load curves and the information that we gathered. It must be very much helpful in order to do the load, in order to find the demand of a particular day, say particular year or particular month, particular year. We can able to comment on that particular pattern. So let's start with a new problem. It is seen that a power station has to meet the following demand. Group A, 200 kilowatt between 8 a.m. and 6 p.m. Group B, 100 kilowatt between 6 a.m. and 10 a.m. Group C, 50 kilowatt between 6 a.m. and 10 a.m. Group D, 100 kilowatt between 10 a.m. and 6 p.m. and then between 6 p.m. and 6 a.m. and then between 6 p.m. and 6 a.m. So plot the daily load curve and determine diversity factor, units generated per day, load factor. Again, this is totally depend upon you, how you can able to design in the easiest way in order to find the load curve. Let's start. Now what I am designing, I am taking the time column here. I am taking the time column. Now I am designing in such a way. Time in hours. So this design is totally up to you. Which one is easier to you, you can approach towards that particular design. So we have four groups that we have seen: group A, group B, group C, and group D. So I am writing group A, group B, group C, and group D. That four group we have. Okay. So let us, if I go through that particular problem once again, it is seen that 8 a.m. to 6 p.m., 6 a.m. to 10 a.m., 6 a.m. to 10 a.m., 10 a.m. and 6 p.m. and then between 6 p.m. and 6 a.m. So now I have divided the time hours in that pattern. 0 to 6. This again I am saying it is totally up to you. 6 to 8, which is the easiest option you can approach. 8 to 10. I am doing this with this approach. 10 to 18. 18 to, but you have to cover all those while designing. You must be remember that you have to cover all those 24 hours and the load demands for each group A, group B, group C, and group D. So group A, for the group A, just go through that, is 200 kilowatt between 8 a.m. and 6 p.m. From 8 a.m. to 6 p.m. it is 200 kilowatt. So from 8, it is given that from 8 a.m. to 6 p.m. means this is from 8 a.m. to 10 a.m. it is 200 kilowatt, and also from 8 to 6, 8 a.m. to 6 p.m., 8 to 10, and also 10 to 6 p.m. It is also 200 kilowatt. Okay. For the group A, it is not operating in that particular zone. Group A is not operating in that particular time period. Let us take the group B. Group B is given 100 kilowatt between 6 a.m. and 10 a.m. 6 a.m. and 10 a.m. From 6 a.m. to 10 a.m. means from group B from 6 to 8 it will operate as 100 kilowatt, and from 8 to 10 it will operate as 100 kilowatt. From 6 a.m. to 10 a.m. Since this our group B is not working. From 6 a.m. to 10 a.m. Okay. Now group C 50 kilowatt between 6 a.m. and 10 a.m. 6 a.m. and 10 a.m. 50 kilowatt. It will be same like group C. From 6 to 8 and from 8 to 10. From 6 to 10. And rest it is not working. Rest of the hours. Okay. Now next, the group D. It is 10 kilowatt between 10 a.m. and 6 p.m. From 10 a.m. to 6 p.m. it is 10 kilowatt. So first I draw the from 10 a.m. to 6 p.m. Okay, then I will go for the next part. Just understand 10 kilowatt between 10 a.m. and 6 p.m. So just first part, 10 a.m. to 6 p.m. This part, it is working as 100 kilowatt. Okay, from 10 a.m. to 6 p.m. Now, and then between 6 p.m. and 6 a.m. means 6 p.m. to 6 a.m. From 6 p.m. night to 6 a.m. morning. Okay, means this is from here from 6 p.m. to 12 p.m. from 12 p.m. to 6 a.m. means this, because it is clearly given that between 6 p.m. and 6 a.m. means 6 p.m. to 12 p.m. from 12 p.m. to 6 a.m. and also between 10 a.m. to 6 p.m. This one. So I have covered all the demands. You have to cover all the demands of the consumer from the power station, and that is you have to design. Okay. So now I am just summing up. Means I have to go through the total load on the power station. Total load. Total load on the power station. Okay. So what is the total load? So for this part, this is 100 kilowatt. This one is 150 kilowatt. Just summing, this one is 350 kilowatt. This one is 300 kilowatt. And this one is 100 kilowatt. So just summing up that total load demand of the power station. So if by summing up the total load demand of the power station, so our first problem that is given, what is our first problem? What is the first problem is the, so that you can easily find which one is our maximum demand from those demands. So it is clear that our maximum demand is this one, 350 is our maximum demand. This is our maximum demand, 350 kilowatt. Okay. So what is our first problem? Our first problem is given is the diversity factor. So in order to find the diversity factor, we have to go through the diversity factor is the ratio of sum of the individual maximum demand divided by maximum demand of the station. So we have already found the maximum demand of the station is 350. So what is the sum of the individual demands? It is 200 plus 100 plus 50 plus 100. Okay. So this is 450 kilowatt is the individual maximum demand. Okay. So what is the diversity factor? Individual demands are, some of the individual demands means 200, it is clearly given in the mathematical problem, plus 100 plus 50 plus 100 divided by the maximum demand is 350. So it is 450 by 350 and the value is the of the diversity factor is 1.286. 1.286. Okay. And sum of the individual demands 200 plus 100 plus 50 plus 100 divided by the maximum demand of the station is the 350. So our second problem is units generated per day. You can easily draw the load curve in order to find the units generated per day. You can easily draw the load curve. And another way, we have easily done that particular part also. It is 100 into 6 hours, 150 into 2, 8 minus 6, 350 into 10 minus 8, 2, 300 into 18 minus 10, 8, 100 into 24 minus 18, 6. That is 4600 kilowatt hour, the unit generated per day. You can easily draw the load curve. You can easily draw the load curve. Again, this load curve is given as from 0 to, this totally depend upon you. So I just, they have drawn it in a different way. So now what I have told that I can draw the load curve in different manner. So I am now drawing, taking those data, I am drawing my load curve. Okay. I am now drawing my load curve. Okay, now how I am draw my load curve. Okay, taking those data, I am drawing my load curve. We all know this is the time means hours, and this is the load in kilowatt. So taking 50 intervals, this is 0, this is 50, this is 100, 100, 150 to the top, 200, 250, 300, and at the top is 350. Okay, so this is 350. So time division I am taking by myself. Simplification I have calculated previously from 0 to 6. I have to cover the 24 hours. Okay, I have to cover the 24 hours. Say from 0 to 6, 6 to 12, 12 to 18, 18 to 24. Let us draw it. From 0 to 6. Okay. So now when I try to draw it, that what I am saying that if I draw it by taking 0 to 6, the values that we are getting from the cycle, we cannot able to compute those values. So rather than doing it, we just take an uniform way, scaling it down in 4, because we are facing some problems here. Now we are taking that, just take as a 4, just take as 8, it is take as 12, it is take as another is take 16, another is take 20, and another is taking 24. That is why I am taking the 6 division to give an indication that all time, depending upon the load and the consumer demand, you cannot take 6 division. Okay, so rather than this is 4, this is 8, this is 12, this is 16, this is 20, and this is 24, because we cannot go for the 6 division all time, because there's a load difference at different but different times hour. It is not an equivalent space. So all the gaps of the times hour are not 2, are not 6, are not 8. So rather than going it, we have to take the small divisions. You can go for the 0 to 2 to 4, 4 to 8. It can be possible. Okay. So now from 0 to 6, it is 100 kilowatt. Means it is 100 kilowatt from 0 to 6. Means this midpoint is a 6. Okay. So now from 6 to 8, it is 150. From 6 to 8, it is 150. From 8 to 10, it is 350. From 8 to 10, it is 350. Go to the peak. From 8 to 10. From 10 to 18, it is 300. From 10 to 18 means this portion. You can take the division number 2. From 10 to 18, it is 300, which is come down like that, and it is going from 10 to 18. Okay. Now, from 18 to 24, it is 100 kilowatt. Means from here to here, it is 100 kilowatt. It is come down here. It is come down here, and it is going equal to 24. So this is the total. This is the total. It will be come down to 100. And So we can find the total area under the graph. It is from 18. So this is the area under the graph. The first area, the second area, third area, the fourth area, and the fifth area. So what is the total area? Total area is the 6 into 100. First one. Second one is the 150 into 2. Third one is the 350 into 2. The third one, 350 into 2. 2 means from 10 minus 8 it is 2. Previous case it was 8 minus 6 equal to 2. Okay. The fourth one is 18 minus 10, which is 8. So it is 300 into 8. And the last one is 24 minus 24, 4 into 100. This is the total energy produced. So if I take the small scale value, say the gap of the timers is 2, this is very much possible for us. But the graph will be different, but we can easily find the graph. It is 4600 kilowatt into hour. Okay. If it is a scale down to the 2 time, we can easily possible. But when I scale down to 6, we can see the problem that we are facing. So again, we can scale down to 4, we can scale down to 2 also. So third portion is the second portion is done, units generated per day. Third portion is the load factor. So load factor is the average load by the maximum demand. Okay. So average load by maximum demand. So what is our average load? Average load can be found, the total load that we have get from the load curve, 4600 by 24, the total hours, 4600 by 24, total hours. It will found the value is 191.7 kilowatt. So what is the load factor? Load factor is the average load by the maximum demand. So average load is 191.7 by the maximum demand. We have seen from the graph is 350. So the load factor is, if I multiply with 100 in case of the percentage, if I convert it into the percentage, so the load factor will found here. So the load factor will found just directly written as 54.8%. So we have to understand this particular problem. Now we are going to another problem. A problem is given that a power station has a daily load cycle as under 260 megawatt for 6 hours, 200 megawatt for 8 hours, 160 megawatt for 4 hours, and 100 megawatt for 6 hours. If the power station is equipped with 4 sets of 75 megawatt each, calculate number 1 daily load factor, Number two, plant capacity factor. And number three, daily requirement of the calorific value of oil used were 10,000 kilocalorie per kg, and the average heat rate of the station were 2860 kilocalorie per kilowatt hour. So our first is the daily load factor. So daily load factor can be found by the total generation of the units supplied per day. It is 260 into 6, 200 into 8, 160 into 4, and 100 into 6. If I take 10 to the power 3 as a common, means we have to convert the megawatt into kilowatt hour. It is found that 4400 into 10 to the power 3 kilowatt hour. And the maximum demand is found from that particular example is 260 megawatt hour. So what is the daily load factor? So daily load factor can be calculated by the total generation unit supply 4400 into 10 to the power 3 into 10 to the power 3 divided by maximum demand 260 into 10 to the power 3 into 24 into 100 in percentage is equal to 70.5%. So number two is the plant capacity factor. So what is the average demand per day? Average demand per day is calculated by the total demand 4400 into 10 to the power 3 by 23 equal to 1 a by 24. 440 into 10 to the power 23 by 24, 24 hours a day is given that 183333 kilowatt. So what is the station capacity? Station capacity is found in, it is given that if the power station is equipped with 4 sets of 75 megawatt each, means 75 into 4 into 10 to the power 3 is 300 into 10 to the power 3 kilowatt. So what is the plant capacity factor? Plant capacity factor is average demand per day, means 1883333 183,333 divided by 300 into 10 to the power 3 into 100 in percentage is 61.1%. So the third is the given daily requirement of the calorific value of an oil used where 10,000 kilocalorie per kg and the average heat rate of the station were 2860 kilocalorie per kilowatt hour. So it is found that heat required per day amount of heat required is equal to plant heat rate into units per day. So plant heat rate is given 2860 kilocalorie per hour, kilocalorie per kilowatt hour, means for 1 kilowatt hour it is 2860. Now what is for 4400 into 10 to the power 3 kilowatt hour? It is the multiplication, total kilocalorie. So what is the fuel required per day? Means it is given that it is 10,000 kilocalorie per kg. So means total 2860 into 4400 into 10 to the power 3 divided by 10,000. It will give 1258.4 into 10 to the power 3 kg equal to 1258.4 tons. This is the another problem that we have solved regarding the fuel required per day in a power plant. So today we have learned a load curve, so, along with the time scaling, which time scaling is suitable to draw our load curve, and also the requirement of fuel per day in a power plant. Thank you.